Welcome to the presentation of the paper Dimensionality Reduction using PCA and CUR Algorithm for a data COVID-19 test. The authors are Marco Enriquez, Samantha Naranjo, Isidro Amaro, and Franklin Camacho. All of them are members of Yache Tech University, School of Mathematical and Computational Sciences, Urcuqui, Ecuador. Here is the outline of the presentation, which is mainly divided in 4 sections. Introduction, materials and methods, results and discussions, and conclusions. Let's start with the introduction. The World Health Organization declared COVID-19 outbreak as a pandemic on March 11, 2020, and people's lives have changed dramatically ever since. There are 2 kinds of tests that can show us if a person is infected or not. Reverse transcription polymerase chain reaction, RT-PCR, and serology test, also known as rapid test. The former is a diagnostic test that, from a respiratory sample of a person suspected of being infected, detects the presence of SARS-CoV-2 virus RNA, and the latter, through a blood sample, is able to detect antibodies generated by the immune system. In Ecuador, the number of cases is still increasing, and according to Ministerio de Salud Pública Ecuador, 495,852 RT-PCR tests has been performed until October 19, 2020. The purpose of this research is to compare the results given by the application of 2 multivariate statistical techniques, principal component analysis, PCA, and CUR algorithm, to a database related to COVID-19 in Imbabura, Ecuador. Then, our main objective is to use multivariate statistical techniques to reduce the dimension of the problem to determine which of the variables of the data set are more significant. In order to achieve this, we have to analyze our data set using PCA and CUR algorithm, and then interpret the results obtained by both techniques. Moreover, we will determine which technique is more effective to reduce the dimension for our data set. Our hypothesis is that CUR algorithm is more effective than PCA. In the materials and methods section, we will first describe the data used. This data was obtained from a clinical laboratory in Ibarra, Ecuador, called Laboratorio Clínico Clínica Ibarra. The test of 256 individuals were performed from May 17, 2020 to June 26, 2020. The variables of this data are edad, IgG, IgM, dímero D, ferritina, PCT, and PCR. But only 2 of them are specialized for COVID-19, IgG and IgM. Here we show what each variable is about. Now let's talk about the techniques of the analysis. In many disciplines and data analysis application, the use of data matrices with a huge number of columns or rows is common, but sometimes the studies with a large dimension of data matrix have similar or contradictory results. In such cases, it's necessary to employ some dimensionality reduction method in order to avoid wrong conclusions. In this research, we use only 2 of these techniques, principal component analysis and CUR algorithm. In the case of PCA, according to Rencher and Christensen, the idea of this method is to create a new kind of variables called principal components, PC. The principal components associated with the largest singular values have strong optimality properties, and they can often be quite useful as a tool to summarize and identify major patterns of data. In equation 1, we can see that principal components are linear combination of the original variables of the data matrix X. We use them to create a new matrix called T that has a lower dimension. However, the ability to interpret the random variables X sub I, or equivalently the columns of X, in no guarantees an ability to interpret linear combination of them. For that reason, we use the CUR matrix decomposition, which is also a dimensionality reduction method that was developed by Mahoney and Dreamis. We use this technique in our dataset because it can solve the disadvantage of PCA with interpretation. The idea behind CUR is to decompose the data matrix X into the product of 3 matrices, C, U, and R, where the C matrix contains a small number of columns of X. The R matrix contains a small number of rows of X. And the matrix U is the product of their more Penrose cell inverses with X. The role of U is to guarantee that the product CUR is close to X. Here, the R-code implementation of the CUR matrix decomposition is referred to as CUR algorithm. This implementation is in the RCUB package, which is available for free in an article of Fodor et al. In the RCUB package, a primary function that makes the decomposition called CUR is implemented. The inputs of this function are the data matrix X, the column parameter C, the row parameter R, and the rank parameter K. To select the column of X to include in C, and similarly for the row selection of R, we had to compute an importance score of each column of X. Then by using the rank parameter K and the data matrix X, the CUR algorithm randomly samples a small number of columns from X using that score as an important sampling probability distribution. Equation 4 shows us the formula of the leverage scores. Therefore, the steps of the CUR algorithm can be written as follows. Get data matrix X and the two parameters C and K. 2. Calculate the leverage scores using X and K. 3. Make a pass over the columns of the matrix and give the columns with the probability minimum C multiplied by the leverage score and 1. If we have chosen at least one column, return a matrix C consisting of those chosen columns. If we have not chosen any column, then go back to step 3. To reduce the dimensionality of the data matrix, simply is to throw away part of the data. Hence, to measure this loss, here is a proposed statistic to measure the performance of CUR algorithm relative to PCA by computing how much variance we lost, or equivalently, how much variance we retained. Since neither CUR algorithm nor PCA can do better than retaining 100% more variance than the other, then E is between -1 and 1. Therefore, if E is close to -1, PCA is more effective. If E is close to 1, CUR is more effective. Now, let's show us the results that we get after applying PCA and CUR algorithm for our data matrix. To use PCA, the variables of the data matrix have to be correlated. This happens to our data matrix because the determinant of the correlation matrix is relatively close to 0. Thus, we have applied PCA on the original data matrix X, which has 7 columns and 256 rows. We can see that the cumulative proportion of the third principal component amounts to 0.8023 of the total variance. Since the criteria we are using to retain components is to account 80% of the variance, we take PC1, PC2, and PC3. We get the same results if, instead of using the previous criteria, we take principal components such that the eigenvalues are greater than or equal to 1. In any case, we retain 3 principal components. PCA also gives us the coordinates of each of the 7 variables using to the principal components. These coordinates, along with the coordinates of each individual and the retained principal components, are used to get the following plot. In this figure, we can see that people on the left-hand side of the plot are similar to each other, and that they are people who tested negative for COVID-19. We can also notice that all of the 7 variables are positively correlated. That is, if one of the variables is high and far from its normal value, then it's more likely that the other variables have a high values as well. On one hand, there is a high positive correlation among ferritin, D-dimer, IgG. Similarly, among PCT, CRP, and IgM. On the other hand, the age has a high correlation among ferritin, D-dimer, and IgG. but it has a relatively low correlation among PCT and CRP. Moreover, the correlation between the age and IgM is significantly slow. That is, its value is rather close to zero. This shows that the higher the age, the higher the values of the variables. We can further notice that the people on the upper right of the graph have high values of ferritin, D-dimer, and IgG, while people of the bottom right have high values of PCT, CRP, and IgM. Unlike PCA, we must provide CUR algorithm with the values C and K. To improve the efficiency of CUR algorithm with respect to PCA, we ran the function CUR with an input parameter C equal K equal 3. Recall that the data matrix is decomposed into three matrices, C, U, and R. Here is a plot of the raw leverage score. We can see that the algorithm returns a matrix R of dimension 134 times 7. That is, 119 individuals of the original matrix were omitted because they do not provide as much information, that is, low raw leverage scores, as the other entries. When it comes to matrix C, we can see that it provides us with more information about the dimensionality reduction. This figure is a plot of the column leverage score. On one hand, the age, D-dimer, ferritin, and CRP have the highest values. On the other hand, PCT, IgM, and IgG have the lowest values. These facts prove that the variables IgG and IgM are not very reliable clinical tests. Note that the leverage score of age is greater than that of CRP. As we choose the column parameter C equal 3, the most natural thing would be to think that the CUR algorithm will choose the variables with the highest leverage score, the age, D-dimer, and ferritin. However, the algorithm returns a 256 times 3 matrix, whose columns are D-dimer, ferritin, and CRP. The variable age was omitted by the algorithm. This happens because when PCA was performed, ferritin, D-dimer, and CRP turned out to be more important to the first principal component, while the age is more important for the second principal component. About the effectiveness, we get that E is equal to 0.9992723, which is rather close to 1. This implies that for our data matrix, CUR algorithm excels in dimensionality reduction. That is, it's better than PCA. In order to show that the choice of the three variables was correct, we run PCA on the matrix C and the matrix given by the four variables. We compute the cophonetic correlation coefficients. With the left plot, we got a coefficient of 0.995, but with the right plot, the coefficient is 0.955. This implies that D-dimer, ferritin, and CRP are the most important variables. Furthermore, on the left plot, we see that ferritin, D-dimer, and CRP are positively correlated, that the proportion of the variance is high. Unlike the left plot, right plot shows that when we add the age, the variance is lower than, and that this variable is barely related with the other three variables. Through this presentation, we focus on reduction techniques and how we can use them to contribute more information about the detection of the virus SARS-CoV-2, which is the COVID-19. Of the conclusions, we consider two techniques, PCA and CUR algorithm. Either to do the PCA create variables at specific components, while CUR algorithm removes less important variables based on the leverage score. Unlike PCA, and whenever it's possible, CUR algorithm allow us to have a better interpretation of the result because matrix C is built from the original variables. After applying PCA for our data matrix, we found out that it's possible to retain three principal components, but they do not give as much information about the variables. Then we ran CUR algorithm with input parameters c equal k equal 3. 3 variables were chosen by the CUR algorithm. These variables are D-dimer, ferritin, and CRP. Furthermore, for our data matrix, CUR retains more variance than PCA. This means that CUR algorithm was more effective than PCA. This explanatory data analysis leads us to the conclusion that the laboratory tests D-dimer, ferritin, and CRP are the most significant in our data set, and they come in handy in the detection of SARS-CoV-2. For that reason, and taking account that COVID-19 is a new disease, we suggest clinical research related to the detection of SARS-CoV-2 to consider them. We did not appraise other values of C and K, other than the number of retained principal components. Analyzing how the effectiveness of both techniques behaves when those values vary and using a bigger data matrix may constitute the object of future studies. Here are the references used for this research. Thanks for your attention.